Good afternoon, everyone. Hope I am audible. Thank you. So, in the previous session, we looked into the our shift registers and counters. Now, the important concepts of finite state machine. Okay, so we will uh, go through the concepts of this finite state machine today. So, what is this finite state machine? Okay, this finite state machine, it is a sequential digital system that transition through a finite number of states based on the inputs and the clock events. So, based on my input and my clock, this finite state machine, it changes its states from one state to another depending on the input. Okay, so input on the clock events. So it is a digital system design. Okay, it is a digital design, and it state dependent controller, because many systems behaves as state dependent controller. For example, if you take the traffic light controller, when there is a one state, okay, of red state, and it will be there for a particular time, then it changes its state to yellow, then it changes its state to green, then from green it changes its state. Something is an example. So the controller dependent on the state. Okay, so like vending machine, elevator controller, UART protocol, SPI I2C, washing machine, sequence detectors, that we will see as an example, and tomorrow topic is fully on the sequential detector. And then control units. So the output depends on the current states and sometimes on the inputs. Okay, that we will try to look into it, because there are two types of uh, machines, state machines, Mealy and Moore machines. Okay, so we will try to look into it, how. But anyhow, it is going to depend upon the state, and sometimes it will be depend upon on the input also. So on this state, depending on the input, the output may change, or the output might be in the same thing. So depending on these three factors, okay, we have an Mealy and Moore machines. Okay, so you will come to know it after a while. Okay, now the question is, why we need the finite state machine? See, the combinational logic depends on the current input. Sequential system requires the previous event. Okay. So, for example, there is a password lock. Okay. So, first, there is a password lock. We want to go and enter, we want to unlock it. Okay. So, if the first digit is correct, it moves to the next digit. If the first digit itself wrong, again it will go and reset it. So we need a state, so a complete sequence, and it will go and unlock. So for this behavior, you need a memory, a decision logic, and a controlled state transition. Okay, so it need, okay, see, if the first digit is correct, it will move to the next state, and if that is also correct, it will move to the next state. If that is correct, it will move to the next state, and it will go and unlock it. If something is happened, it will go for a reset. So we have a state. Okay, so to hold the state, we need memory, decision logic, controlled state machines. So to implement these behaviors, please try to understand, to implement this behavior, this FSM provide a structure. Finite state machine, it provides a structure. Okay, No worries if you are not able to understand this. At the end of the session, you will be able to understand it. I will go on repeat the things. Okay, so no problem. So for this, what is the building block? Okay, so it consists of a state registers. Okay, it consists of a state register. We need a state register which it want to store the present state. Okay, that is implemented by using the flip flop. Okay, then we need a state logic, next state logic. Okay, so this is going to depend on the input and the previous state and the I mean the current state. So what is the next state in the sequential circuit? It depends on the feedback and the current input. So we need a next state. Okay, and we need an output. So the output, okay, output, it might be depend on the input and the previous state. It depends on the what machine we are going to use. Okay, so at the day, what I am trying to tell is, see, it is a sequential circuit only. Okay, it uh, we are trying to understand the finite state machine. Please understand, we are trying to understand the finite state machine. Okay, why? Because using the finite state machine, we can implement our logics. Okay, suppose there is a CPU, they have implemented the CPU with the finite state machines. Okay, so we are capturing the behavior and we are putting it in a state level. Okay, so to structure that, we have to understand this finite state machine. So this finite state machine, as it is having a state register and next state things and an output. Okay, this output may depend on the input and then the uh, the state where it goes. Okay, so still it will be like a confusing stuff only, I know it. Okay, I am trying to give you an better idea of how you can give it. Still, I didn't complete the finite state machine. Maybe it takes a little while. Okay, so you do with me. State concept. A state represents the. So now we know that for the finite state machine, we need some the state and then the next state and then the output, something we need. So the state concept is, a state represents the current condition or the mode of operation. Okay, so for example, at the current state it might be red for or green or yellow. So there is a state. So first we want to define the state. That is very much important. First we want to define the states. Okay, so either state 1 or state 2 or state 0 or state 3. Okay, these things we have to decide it. That is what I'm trying to tell. So FSM remains in one state until transition condition occurs. So a finite state machine which is having a state, it will be in one particular state until a transition condition occurs. Otherwise, it will be in this state. That is where the state concept. So that means unless it's some condition occurs, it might change the state or it will be in the same state. That is what I'm trying to tell. After 3 to 4 slides, when we try to do an example, you guys will be getting an better idea. Now the state transition. So now we have a state 0, state 1 and state 2. Okay, suppose if it is in state 1, FSM is in state 1. Okay, so whether it want to be go to another state It depends on the clock and the input condition. Okay, so what is the input and when the clock is appearing, it depends on this. That is where the state transition. Okay, example, first it will be in an ideal state, and when we try to give an input, that means start, so it will be start state, it will move into the start state, and depending on the clock and the input, it will go and do the process, and then it can move to the done state, and then again it will come to the ideal state. So each transition follows a definite rule. Okay, suppose from ideal state, okay, there will be a condition, it want to move only to a start state. When there is an ideal state, from ideal state it can go only to start state. So that is means a defined rule has been stuff. From the start state, okay, either it can go to done state or an process state. That is also defined rules depending on our application. Okay, that is what the state transition. So the finite state machine, the first thing as it has a state. Second thing, it want to move from one state to another state. That is called state transition. Okay, that will happen depending upon the clock and the input condition, and that is predefined. That we will predefined when we try to design our system. That is what I'm trying. This is also we will design, this is also we will design. Okay, that is what I'm trying to tell. Now the characteristics, okay, the characteristics of finite state machines, it has finite number of states. You cannot have up to infinite states. Okay, there must be a finite state. Suppose you want to create one system. If you want to create a one system, that system can move from one state to another state. Depending on the state, it will give the output. That is the another stuff. And the what all the state it is present inside, no, that want to be finite number, and it is a deterministic. It is not somewhere either it goes here, either that goes. No, it, if this is the input and if this is the clock and if this is the current state, it want to move to this. That is predefined, and it need a state memory to hold the current state, and it want to be clock driven. Only through the clock, whenever the clock trigger it happen, it will go on to change the state, and the output is predictable. And main thing is it want to synthesizable. That means simply only we can write a program. No, you have to convert that into a hardware level. That is where the synthesizable. So those all are the characteristics of FSM. If it is not having these characteristics, then it is not an FSM. That is what I am trying to tell. Okay. Now we are trying to somehow we tried to understand what is finite state machine. So there is a state, and it can change the state. Okay, it can change the state, and it is predetermined, and it is something deterministic. All these things it want to go and behave. So now this machine, there are two types of machines. One is Moore machine, another one is Mealy machines. So now we will try to understand this, what is Moore machine and Mealy machine. Okay, so when you try to apply a finite state machine, either you can derive the Moore machine or an Mealy machine. You try to understand. So how, what is the difference of this Moore machine and Mealy finite state machine? Okay, so I told there is a state memory, there is a next state logic, and there is an output logic. Okay, now you see the Moore machine, this output depends only on the present state. If the present state is S0, okay, if the present state is S0, if we fix the S0, the output is 0 means it is fixed. Whenever the state machine comes to this S0 state, the output is 0 only. Suppose if it is moving to S1, if we keep output as 1, whenever this machine come to this state, the output is 1. However the input might be, depending on the input, it might be changing the state or whatever the thing. Okay, for example, in a traffic light, okay, there are 3 states, S0, S1 and S2. So when it's there in S0, it will be always red. When it moves to S1, it will always yellow. And when it moves to S2, it will be always green. That's it. Depending on the time, it will change. It will change. Okay. So the output is fixed to the state. That means for one state, that output is fixed. That is where the Moore machine it is telling. When you try to change, when I try to see this diagram, okay, the output logic, try to understand, okay, is going to depend upon only on the present state. Input is not there. You try to understand. This out, it is going as a feedback only. It is not coming like this. So the output is going to depend upon only on the state, present state. So whatever the present state, according to that you will get the output. Or else in another word, how you can keep it is, for each and every state, the output is fixed. That's it. For every state, the output is fixed. Something, it is not like 1, you can keep it as 0. That is what? Depending on the input, whether it can change the state or not, that is different. But in the Moore machine, the output for the state is fixed. That is what you have to understand. Okay. For example, you can take, because for one state, the output is fixed for the traffic light. Because for this state, it want to be red. For this state, it want to be yellow. For this state, it want to be green. That's it. No other thing. So this is called the Moore machine. Okay, Moore machine. Now, what is its characteristics? Because since the output is going to depend upon only on the state, that output is stable. You have a stable output and simpler timing, and output changes only in the clock edge. That means the state changes happening. That's it. So predictable, only fewer glitches it will happen. But in order to do this, we need more state. In order to implement this, you need more state. So whenever we try to implement the Moore machine, you need more number of states. Now comes Mealy machine. Sir, what you are trying to tell with the Mealy machine? Okay. So the output, see, you always try to think of this. The output is going to depend upon this is the present state and the input and the current input. So depending on this, the output changes for the state. Okay, that means the output is not fixed for one particular state. The output is changing depending on the current state. So since it is in this state, for this current state, the output may be 0 or the output may be 1 depending on the input, current input. So depending on the state and then the input, the output defines. At first it looks something awkward, but okay, no problem, no worries. When we try to solve one problem, you guys will be able to understand it. Okay, so the mathematical concept what they were trying to, previously it is only with the state, that is what Moore machine. In the Mealy machine, the input is joining it together. Okay, so the output is going to depend upon both the state and the input. For example, vending machine, if you want to see in the vending machine, if you want to uh, 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 paid 15 rupees, okay, but you have only 5 rupee coin, 3 5 rupees coins. Please try to understand. Okay, you have 3 5 rupees coins. Now, to get the product, to get the item back, first you insert 5 rupee coin. So the output is going to depend upon the current state and the current input. So the current state, you will be having one state, and the current input 5 rupees we went and used it. So if we need that product is 15 rupees, it is waiting for another. So next you will put 5 rupee coin again. So now you have one more state. Okay, that means it is, there is a state, and then again we are putting the input. So the output is going to depend upon the state and the input. Now it will not, the product will not come out. Then again if you are putting 5, okay, now it changed to the other state, and depending on the current input, since these two states, from this it went to this state, from which it went to this state, and now we put the thing, and the output, since 5 15 has been got it because of the input, current input, and this product will come out. So it will open, it will unlock, and you will be able to get that item. So that is where one analogy where you can try to understand about the Mealy machine. So vending machine dispense signal depends on the inserted coin plus the current state. So you see, for example, if we keep for this state, if we have only this output, for this state, if we have only this output, okay, likewise if we keep, that will not be a good thing. So they went and used vending machine, the current input what we are giving, and depending on the state, so we can go and it is depending on these things. Okay, so this is what about the Mealy machine. Okay, now it is faster responses, it is having only fewer state, and it is compact to implementation and immediate output response. But you can have a possible glitches because of the input, no, because of input, depending on the current input, because at the current input it might be having changing, so there will be a possible many glitches compared to the Moore machine. Okay, so now when we try to do the comparison, it is depending on the state only, state plus input. It is slower because it is having more states, it is faster. Glitch risk is low and it is having higher. Number of states more and it is fewer, I told. Timing simplicity, it is easier, it is harder when we try to go and use a timing analysis. So now how are we going to design our, state machine? First, this step is very much important. You have to understand the problem to solving the finite state machine. It is not in the hardware, even in the software also you can go and use this finite state machine stuff. Okay, so you have to understand the problem. Then to that problem, you have to define the states. S1, S0 state, S1 state, S2 state, S3 states. We want to define it. That is very much important. We want to define the states for the problem. Then what are the input? Depending on the inputs also we have to define, and outputs also we have to define. Then try to draw the diagram and try to solve that problem using the defined states and input output, and draw the state diagrams. Once you draw the state diagram, you try to create a state table, and from the state table rest is easy. Okay, instead of, suppose if we have 3 states, so 3 states you can represent by using 2 bits, like 00 is this state, 10 is this state, and 01 is this state. And suppose if we have one more state, we can represent by using the binary implementation. Okay, and after that we want to implement the, whenever if we try to put the state diagram, this and all very much easy. These and all implemental RTL, for that you need the VLSI code and all such kind of things, and verify with the simulation. These things and all will be easy if you are able to do this state diagram. Okay, so that is the steps which we want to understand. Okay, so what is the meaning of the state diagram? It is the graphical representation of the finite state machine. When we try to derive something, that is a graphical representation of that. So usually we will put circles and arrow to transition, and label the input and then output, input and output. Okay, something like this. We will go and label input or output likewise. Okay, example is a sequence detector. So by the example we will try to understand the stuffs. Okay, so today and tomorrow, by today and tomorrow, our aim is to understand the finite state machine. This is very much important in project creation or whatever the things we are going to use it. Okay, so no worry, if you are not able to understand, still you have time, no problem. Okay, no problem. If this is the first time you are listening to it, I know it is difficult to understand, no problem. But if you try to get an idea about it, this sequence detector, then you can understand the exact thing what I was trying to tell, the story which I was trying to deliver, now till now you can able to understand it. Okay, so now let us try to understand this by solving a problem. Okay, 101 sequence detector. I have a machine. Please try to understand. I am going to give a serial inputs 1 1 0 0 1. That will get an input continuously. If it's going to get an input, and if it finds this pattern 101, it will give 1 as an output. Otherwise, it will give a 0 as an output. This is the system I am going to design. Try to understand the problem. The first step is very much important. You guys want to understand the problem. Okay, you guys want to understand the problem, so you will be able to understand this finite state machine. The same sequence detector, tomorrow also I will be teaching the same thing, but I will combine all the things, Mealy Moore machine and Mealy Moore machine with overlapping and without overlapping. Okay, with overlapping and without overlapping. That is the main thing. So to understand those things, I am giving you an basics today. I am trying to give you a basics today, so you all can understand the tomorrow's things. Okay, So these 2 sessions is dedicated for the FSM. Today, introduction. Then tomorrow, we will try to solve one problem with only one problem. That problem we will solve for Mealy and Moore, in that overlap, without overlap, overlap and without overlap, and how you can design. Okay, we will go depth inside it. For a time being, now you try to understand something. This is the design, this is the state machine we are going to design it. That means it is an machine. It will get an input of serial ones and zeros, whatever the random value you go and give it. When it finds the sequence 101, it will give one put as 1. When it not finds, it will give 0. Okay, hope you all able to understand this problem. Okay, this is the problem statement. So let's design a machine that searches an incoming stream of bits and sets its output to 1 every time it encounters a pattern 101. For each and every time when it encounters a pattern 101, it will give 1. Okay, we will design a Moore machine first. Okay, that, so what is Moore machine? Depends only on the current state. Okay, the output is going to depend on the current state, and the output label is written inside the state circle. I told already, the output is already defined. However the input, whatever the input, the output is already defined with this. So that will be easy for you all understand. Then tomorrow we will try to understand the Mealy machine with that. Okay, so this is about some understanding the stuff. Okay, so we will have a state 0. Okay, it is going to be a tough to reading this, I know it. Okay, let me make it as simple for you guys. Okay, let me make it as simple so that you will be able to understand it. For that, let me open the another annotator, MPX. Okay, I am going to take an annotator. I hope you guys able to understand the problem. I hope you are able to understand the problem. Okay, so now what I am trying to give is, we have a sequence of numbers is coming. Okay, and if it encounters 101, we want to output 1, or else output is 0. Okay, that is the idea. So now we want to define the state. How are we going to define the state? Before defining the state, we want to know that whether we are going to use Moore machine or Mealy machine. Okay, so for a time being, you understand we are going to use only a Moore machine. So what is this Moore machine? It is telling, Moore machine tells that the output is fixed for state. Suppose we have S0 state, means the output is 0 or 1, it is already fixed. And if it is S1, the output is fixed. If it is S2, output is fixed. So likewise, we have to go and do the things. Okay, so now our problem is, we want to deduct. So somehow the input is coming. Somehow the input is coming to us. Yes, of course, correct. I told we want to define the state. Okay, so our aim is to find 101. Please try to understand. Our aim is to find 101. For that, we have to define this state. Okay, now let me tell, create a state called S0. Okay, since all the input will come through the S0 state, all the input will come through the S0 state, and okay, now I am maintaining the output as 0. Why I am putting output of 0? Because only one bit has been received now. So I want to receive 101. Then only I can put 1. Since the S1 is receiving only 1 bit, I cannot go and conclude the output. So I am making it as 0 because that is the thing. So only 1 bit. Now the input. If the input is 1, let it go to the another state. Something like S1 state. Okay. If the input is 1. Suppose if the input is 0, then it don't want to go to the other state. Let it be in the same state. Okay. So when we try to get the input, it might be randomly coming, and then we are trying to check if the input is 1, let it move to second state. That means already we know there is a 1. If there is 0, let it stuck over here only. Okay, so we are able to complete this state. Now in the S1 state, you try to understand in the S1 state, that means if the machine come to S1 state means it has deducted the 1. It has went and deducted 1. That is the stuff. So here, when it comes to here, it has deducted 1. And since it has deducted 1, it is only 1 bit. So we cannot give the output as 1. So I am giving it as 0. Please try to understand. Okay. So 1, the first input, this is only at the reset condition, it is coming here. When it is moving, okay, try to understand, when it's getting an input 1, the machine moves to this state. When it is in this state, if the input is 1, okay, already 1 got deducted. If the input is 1, no, then it want to be in the same state only, because I need a condition 101, but I already have 1. But again, if I get 1, I want to be in this state only. And if it is 0, if my input is 0, it is moving it to the other state. It is moving it to the other state. That means when the machine moves to the other state, we received 10. So when the machine is in the second state, it is having 10. 10 is, we found 10. Try to understand. Okay, we found 10, and we have only 2 bits. We have only 2 bits. Try to understand. Now, so for that only we are given 0. Now here, now the machine went to the S2 state. If it is input is 0, now we will get an input to the machine that will be in this state. So if the input is 1, please try to understand, if the input is 1, okay, if the input is 1, it moves to the other state. Okay, I don't want this one. It moves to the other state. There the output is always, whenever the finite state machine moves to the S3, the output is always 1. That means we reached 101. That means the input is 1. Suppose the input is 0 in the S2 state. Suppose, please try to understand, in the S2 state, if the input is 0, that means it will become 100 and it is of useless. So we will move it to the S0 state. If the input is 0, we will move to the S0 state. So this state we finished. Okay. Now in the anyhow in the S3 state, we will get 101. Okay. Whenever it is in the S3 state, you will be getting the output as 1. That is correct. Then suppose in this state, if there is an input we are getting, okay, if we are getting an input as 1, if you are getting the input as 1, that means it want to move to S1 state. And suppose if you are getting input as 0, it will be moving into this state. Why, sir? Already 101 we already deducted, we have got 1 when it moves to the S3 state. Suppose when it's in S3 state, you are getting 0. I mean, you are getting the value as 1. That means 101 is coming there. So there is no overlap pattern for that 1. So we already got 1. Let us move to the S1 state, so that because already the in this state 1 will be getting deducted, then it will go on carry on the things. Suppose instead for 101, if our input is 0, that means there is a chance of again next 101 coming. Okay, it is of overlapping. I told with overlapping. Okay, so now it want to move to the next 0 because this is the thing which has 10. So likewise we try to complete it. So if you are able to solve this problem in an diagrammatic way, okay, that is what explained in this line by line. It has been explained. Okay, I know it is tough to understand, of course. I know it is tough to understand. Screen video is not visible. It is visible, it is fully visible. Somewhere problem with your side, maybe the network problem. Okay, so that is what I captured it over here. Okay, so you guys try to draw the diagram by yourself after the session, not now, after the session, and try to understand it. Okay, then we are capturing it in a state table. So S0 is a reset state. So whenever there is a input 0, it will go to S0, and from S0, whenever the input is 1, it is going to S1, and always the output is 0. So whatever we captured in the diagram, we were trying to put in a table. So S1 means already we received 1, and if there is 0, it is moving to the next state, and if the input is 1, it is remaining in the same state, and we are maintaining the output as 0. Then when it moved to the S2, it is maintaining 1 0. Then we are checking the input is 0 means no. Then we have to go to this S0 state. Again, we have to start from the first. Or else if the input is 1, we found 101, and the output is 0, and we are moving it to S3. Once it reaches 101, output is always 1, and depending on the input, it goes to S2 or S1. So these are the things what we have done in the diagram. We are trying to put it in the state table. Okay, now to this state, I am trying to put an encoding. That means I am trying to apply a logic 0 0 1 0 or 1 1 to the state. So I am trying to put a I am trying to encode the value to that state. I am trying to encode a value to that state. So either you can use binary encoded table, or however you want, you can go on encode. So this is 0 0 0 1 1 0 1 1 state. Okay, this is what the state. So you want to represent the input is 0, and it is in the S0 state, and this is the S1 state. Instead of the alphabetical alphabet, we are trying to represent in the number format. That is where you can able to get the combinational circuits, where you can go and get the expressions. That is what the idea behind it. Okay, so you can express in something like this. Okay, now you can use 1-hot encoding by changing only one bit. There are some techniques. Okay, 1-hot encoding and binary encoding. I'm not going to spend much time on this. Okay, so these and all something to give you an idea, I put it over here. Okay, to give an idea, we put it over here. For very low code, we can go and implement it, no problem. That's not a big deal. Okay, so the same thing we did it for the one hot encoding. Okay, instead of making all as an alphabet, we are trying to put one hot encoding stuff. Okay, so why we need reset? Why an FFM need reset? When a digital circuit powers off, the flip-flop in the state register settles into an unpredictable voltage level. So without reset signal, the FM will not boot into an undefined startup behavior, a unknown state. So causing the circuit to malfunction immediately. So always you try to keep a reset state for an finite state machine. Okay, so something like ideal, whenever it is in reset state, you can keep it as an ideal. Okay, so there we have a synchronous reset and asynchronous reset. I want to go, don't want to go much deep inside it. Okay, if you guys, my expectation is if you are able to understand this 101, okay, if you are able to understand the sequence detector 101, tomorrow also I'm going to be more deep inside this 101 sequence detector. Okay, 101 sequence detector. Tomorrow also I'm going to teach you. Okay, no worries. Okay, so missing reset, incomplete state transition, unintended latches, output glitches, illegal states, unreachable states, race conditions, these all are something the common mistakes we will go and find it in protocol controller, memory controller, bus arbitration, CPU control logic, UART, packet processing, digital controls, where we will be using these finite state machines in the VLSI point of view. Okay, so this is the for the practical design guidelines, synchronous FM, explicit reset, we have to give default transition, safe encoding, register output for critical path. These things we need for the ASIC timing and power optimization is going to be a matter. And for FGA, they will go and use one hot, often preferred. Okay, so these are something, a practical guide that I will give you the PPT. You can go and understand. So our main thing today, our core block is something state register, next state and output logic, Moore machine and Mealy machine, and state diagram, state table, encoding, then RTL and verification. I didn't do it. Once encoding, you can go for RTL and verification encoding. So FFSM are essentials for control logic in modern VLSI design. That's why we are moving into it. So somehow the other way, you have to understand this. You have to understand this this state machine. Okay. So now, as usual, okay. Now the things comes as usual. We will try to understand the state machines. Okay, by a code. A simple. I took it from AI tool. Nothing. I have taken it from the AI tool. Okay. One is for showing the output in the console window, and the other one I did it for the wave purpose by showing it in the EP wave. Okay. So these are the code. Okay. It is overlapping 10. Whatever the problem I solved, that I converted into logic. So accordingly, it is going to give me. So randomly, it is going to, I'm going to use the test bench by using this sequence. If you want to change the sequence, you can go and change and you can do it however you want. But with overlapping, I am able to get the stuffs. Okay. So whatever the thing we learned right now, whatever the stuff we learned right now, okay, whatever the thing we have been learned in a theory of FSM, okay, so here I am trying to maintain the state, okay, initial state, and it is found, and it is found 10, something like that. We are able to keep it, and then we are trying to put in the case state, whether it is in an S0 state or S1 state or S10 state. Okay, those things we are trying to do it. Okay, I think it went and used melee machine. Okay, that we will see it tomorrow. Simply for the sake, I went and used to understand it more clearly. I went and used it for the Moore machine. In the melee machine, we can reduce one state. Okay, so it went and given me an uh, melee machine. You see, melee machine FM. Okay, maybe you can try for Moore machine with 101 uh, sequence detector. Okay, so now you see, this is the test sequence we are trying to give. Okay, so now the data input is 1, data is out. Next, the data output is something, it is going and giving it. Okay, at the 15th second, this is the 12th second, at the 15th second. Okay, here the 5-second clock. Okay, so once the data out, that means you see that 101, so you are getting the 101 at the third thing, you are getting the data as an output, and then again there is a overlap, so you are getting a data as an output, and then when it moves at the last, it is going to do at the last. I think there was a one, I'm not able to put it over here, you see there one. Okay, if you put it over here, no, the last sequence, that it went and deducted. For all other things, it went and put it as 0. Okay, so that we can go and use it. Here, if I try to run it, we can see the same output with the waves. Okay, the same output, we are able to see it through the waves. Okay, what is D in? We are getting it. Okay, D in. And what is the D out? Okay, here we are getting it as 1, here we are getting it as 1. Okay, then what is the D input? We got it. Okay, 1 0 1, so we got that input. Okay, 1 0 1, we got the input as 1. 1 0 1, we got the input as 1. Now 1 0 1, we got the output as 1. So it is easy to understand and the stuff. Sir, why I want to learn this? To understand the finite state machine, this sequence detector is a good example. That is what I'm trying to sell. And you see that always the reset button is on. When it is off means nothing will happen. Okay, and we are able to see the clock over here, and what is the D in and D out, and the clock, and it is the current state it is trying to give, and what is the D out. Okay, so these are something which you can go and analyze the things, so you guys will be having a good idea. Okay, so hope you guys able to got something. I'm not going to end the finite state machine over here. Tomorrow we will go and analyze all 101 sequence with all 4 type. Again, I'm going to tell these things, and with the melee machine, Moore machine, and I'm going to draw the diagrams for all possibilities. So you guys be thorough with the finite state machine, so it will be easy for you all to understand for the next level. Okay, so this is what about the today's session. So you guys, if you have any doubt, please let me know. We can have the you Okay, guys, thank you. See you tomorrow. Tomorrow we will see the same thing with the more deep with all analysis. So meanwhile, you try to go and draw the diagram by yourself. So tomorrow you can understand much better. Okay. Thank you all. See you tomorrow. Bye.